para abrir?
Vou.
A gente não está pronto ainda.
Tá
Pode
bom.
atrasar um pouco?
Pode.
A gente está um pouco atrasado.
Se você quiser, pede para mais.
Estou esperando o ok por lá. It's okay? It's okay? Okay. So, welcome everybody. Again, my name is Nelson Amaral. I'm here to introduce Professor Zuffo. Doesn't need introduction to most of you anymore. Professor Zuffo has been a distinguished researcher in the community in Brazil. He has led many different efforts, including the very key initiative during the pandemic, where his group has done very significant work, saving lives and being very influential during that critical moment in Brazil. But he also is known for a number of other things, including the first Linux-able RISC-V systems. But I see Professor Zuffo, beyond all the technical contributions, as a connector, as someone that connects people with opportunities in many different ways. So thank you for being here. Thank you for hosting us.
Thank you very much. I hope to have a very inspiring conversation this morning. We will split the conversation in two phases. The first phase will be the vision, and then the second will be the reality. Because in the end of the day, particularly in the context of Brazil, we need, and we have our own computers. And that's about my talk today. How we can, in this moment of humanity, we can design anything from a very abstract application idea. I will not say even transistors. I will say materials. Brazil is a continental country built from almost all cultures in this planet, so we have talents. I just learned recently that we are the third biggest reserve on critical materials. So we have everything. And eventually we can do that on a different way. And that's my talk today. I have been influenced in recent years by some key people. One very important person is Bob's. He originally thought about keyboards and later touch screens. But that was the discussions at MIT by the late 60s. And he has this famous phrase: people who are really serious about software should make their own hardware. So for almost 4 years, John, we are trying to develop open software. And my concern along the week, and I'm very happy to have this speak at this point of the conference, the goal is how we should go to the entire stack. We should do everything open. And I do believe in maybe in 10, 20 years, this vision will be effective. And then I have another mentor, that is John Hall. Do it open. So that are the premises of my talk today. We have this incredible achievement that is designing the first open source ISA, that is RISC-V, but the vision is we should go beyond. We should go beyond. We should not stop only in the ISA or the cores. We should go beyond. And I do believe that it will happen. And we are being part of the same revolution that we observe with 3D printers. A few years ago, 3D printers are expensive, clunky, big, hard to achieve. I remember that the first 3D printer that my school bought 20 years ago, it cost $1 million. Now, any 3D printer you can buy for a couple of dollars, maybe $200, $100. So that's part of the vision. So we are CITI, the Interdisciplinary Center on Interactive Technologies. I should say that the original name was even craziest because we do believe in human computing symbiosis. So we doesn't believe that AI will take over humans. I do the opposite. AI will make humans better. I believe that AI is just a step on human evolution. And the evolution of humans and computers, they go through interaction. So higher is in the interaction with computers, better we should be as humans. And our vision is that computers are growing exponentially. If you heard yesterday, RISC-V, only RISC-V ISA, they released 25 billion chips already. Only RISC-V. Imagine now computers being produced by ARM, Intel. So we have a vision that for every human, and we have 8 billion humans in humanity, we will have more than 100,000 computers per human. I was talking Friday with the head of a big truck company worldwide. He said, well, we have the driver on the truck that we manufacture, and only in our truck, we have 2,000 microprocessors to support the driving of that truck. So if we have trillions of computers, we need to have them open. Doesn't make sense in the long term having proprietary technologies embedded in such computers. And going further, we do believe that on trillions of edge AI computers. So AI doesn't imagine only AI in the cloud. We should see the AI everywhere, including in the very tiny devices. You will see my team pursuing the goal of porting LLMs to our chips. And again, everything open. So the AI Internet of Things is a reality. We can see that in cities, digital cities like São Paulo. We have millions of humans and billions of devices. My team are designing AI edge chips for street lights, for police cars, and beyond. But we do believe that Brazil, it will be responsible to save this planet, just because we have the biggest stock of carbon beneath the Amazon forest. So why not? Maybe, could be a talk next year, the Internet of Forest. So today, if we see the cloud, that is the current structure. You know, the big techs are making a lot of money here, but there is a silent revolution at the edge. And I do believe, and you should agree, with everything that we saw today, the Moore law is happening faster in the bottom. Can you imagine, John, Labradors with this performance? How fast is a Labrador compared with a PDP-11? And we have a Labradors in our hands, you know, in my ring. I just discovered that we have a, unfortunately it's not a RISC-V, but there is an open source thing here. The Zephyr operating system is running this ring, you know? So, what is the dream? We do believe that in one day, with open source, RISC-V and things, more computing will go to the bottom, and then the bottom will become relevant. We just need a few more technologies. I will not talk about that today, but that is happening. So if you see a Labrador today, it's faster than any laptop that I had 10 years ago. And just my group, we manufacture 5,000 Labradors. It's easy. We never imagined designing and manufacturing our own computers. And open source lead us to this direction. So, being more formal, there is a trade war. National and countries are designing national policies. China is designing the national policy in semiconductors. US is designing a national policy in semiconductors. And Brazil should design its own semiconductor national policy. And in this window of opportunity, we should understand what is the stack. NIST, the National Institute of Standards and Technology from USA, they preconize the concept of the stack. So all technologies that should be engaged from applications to materials. I'm deeply studying these documents for almost 3 years, and I really agree and I understand that designing ships or designing what we're doing is one of the most complex tasks that humans perform until today. Imagine the amount of human effort, imagine the amount of engineers, and that is the stack. And the thing is, when we saw this stack, how we can design strategies to have a full domain of everything. Our approach is top-down. Everyone here are taking about a bottom-up approach. Okay, we will have foundries, we will design chips, for what? What is our target ecosystem? So I preconize that Brazil should do the opposite way. We should go from applications to materials. And again, we have everything. We just need to organize ourselves, and we should have a robust approach. In engineering, we call paradigm. So I'm talking about new paradigms in this very exciting age, especially for the youngs. I lived during the First Cold War. We saw the Berlin Wall collapsing, the end of the Soviet Union. You boys and girls will tell to your children the time that you live it today. I wish a better, peaceful world, but it's a very exciting moment living at this moment at the humanity. And then we have the opportunities. And the opportunity is, if we see how to make viable this structure, we have a strategy in my group. That is the feasibility and real thing. Our approach is what we call heterogeneous systems co-design. We will see that my guys, they are experts here or there, but they need to navigate everywhere. They need to understand every single material that is the basis of a chip. They need to understand what is silicon carbide, what is silicon arsenide. They need to understand how the periodic table affects everything. Because few people in this room know we are dirtying the whole planet with chips that are highly contaminate electronics. So we need to approach, and Brazil needs to address the problem of sustainable semiconductors that no one is talking about. No one, only Brazil. And the plan is, from applications to platforms, to boards, to chiplets, to wafer materials, metrology. Nowadays, AI is there. Computing became a commodity. And then we need to have approach. And the approach is the heterogeneous systems co-design. So, when we talk about the heterogeneous systems co-design, we start to talk about something that few people mention, and maybe I will be the first mentioning here. The paradigm is what we call 3D chiplets. Doesn't make sense anymore. 3D, it brings several fundamental theoretical problems, because imagine, for 50 years, the whole electronics is 2D. All CD, synopsis, cadence, all open source are 2D. There are some aspects of 3D, but real 3D chiplets is the challenge. And then we need to have this co-design because the paradigm is shifting from single board computers to single chip computers. And that is not a young idea. When I was 23 years old, me and my wife, we moved to England, and we heard about crazy British guys talk about transputers. A computer so small that could be considered a transistor, a fundamental piece to design complex systems. So these ideas doesn't get out from my mind in the past 4 years. 35 now. So the paradigm on 3D chiplets is from single board computers to single chip computers. And I will tell that my group is very close to this paradigm because we have everything. We have the dies, we have the memories. We just need to learn how to assemble them in 3D. And unfortunately, or fortunately, we will need to design the tools to do that because very few companies in the world has this technology. So also, our abstractions, that is a standard architecture. No, we have memory, CPU, GPUs, and then the specialized microprocessors that do matrices, neural networks, and things. For 40 years, we always thought on a plane. We always thought mapping these architectures on a plane. And now we need to move to space. And that is very exciting. That is really exciting. The fundamental problems behind this transition are enormous. Unfortunately, we have critical mass in Brazil doing such kind of research. So, based on these premises, we decide to design and manufacture our own computers. That's a very crazy idea. It's a kind of mad dog idea. John came to us and said, you guys need to design your computers in 2016, right, John? 14. At that time, we visited Professor Patterson at Berkeley. We went to Sci-5. We learned about RISC-V. And we created the Caninos Locals program. We call a program because we want to put in place this vision. From applications to materials, we want to cover everything on a new paradigm named heterogeneous systems co-design. It's a pioneering effort, but the result is in here. We are manufacturing such boards inside the university, totally free. And we should go beyond. So our clear next step is going to the chiplet thing. So the objective of the plan, the program is develop and dissemination of a national single board computer. It will become single chip computer through the design of the advanced microelectronics and creating a family focusing on artificial AI. You know, guys, we have our agro-business sector. We have a forest to protect. We are the most energy efficient country in the world. Almost 90% of our grid came from renewables. With low tech. Imagine if you have high tech. We can do much more. So, thinking about all the universe of applications, the family was based in the 3 boards, the fleas, the Labradors, and Bancars. But now, I should say that the first decision that we always do is choosing a software platform first that will enable everywhere. So in our high-end chips, our decision is choosing Debian. I visited the Debian site yesterday. They said, we are the universal Linux distribution. Because all other distributions, Yocto, Red Hat, Ubuntu, we know that they are all based in Debian, and we are proud because our hardware always carry the state-of-art distributions. So in the Labrador, we are using the Debian 12, the latest of the latest, and the Linux kernel 6.10. Everything designed by our team. So with this open source, we can keep the software up to date to the market. So from the application point of view, it's the same concept of an Apple. You open Apple, users doesn't care what are the intrinsic electronics. And eventually you can change the chip according to your needs. But then you guarantee the whole pipeline, from applications to materials. Final users, citizens, they need final applications. And we have this whole tool, this whole stack, from applications to materials, under control. And our AI framework is running. Our problem here is to guarantee performance with the minimum energy. That's why we focus on Labradors with power supplies that is usually around 2 watts. The question is, it is possible to design GPUs with the same performance, consuming only 1 watt? My answer is yes, if we have a co-design approach. Because energy, you see, along the whole week, no one talked about energy. They doesn't care about energy. They doesn't care about sustainability. But we Brazilians, we care. And the only way to do sustainable, high efficient, low power chips, in my opinion, is having a system co-design approach, where the energy requisite is a fundamental requisite to design these chips. But we also, in our low end, we also used another operating system that is Zephyr. You can learn that both operating systems came from Linux Foundation. Only Zephyr, this year, we have 100,000 commits. What that means, there is a massive community behind Zephyr. We need to bring all these software guys to our hardware community. So the problem of this conference, we need to put the software guys, the open source software guy community, talk with the open hardware community. So, and in this way, we can capture value. Wafers are quite expensive to manufacture, but then you explode in the minimum order from TSMC is 200 wafers, right? The wafers from Labrador today, we have 4,000 chips per wafer. So 200 wafers is around 1 million chips. So it's very expensive to expand, and then you have 1 million chips. And then you start to do everything to reach a data center that, again, costs a lot of money. But usually, to populate a data center with all cores, when we have 1 million chips here, we are talking about 4 million cores. 4 million cores. Usually on a data center, to buy that computers, you need 20,000 cores. So you can imagine the amount of data centers that you can do with a single wafer. And the thing is, how we capture the whole value chain in this process. And then we need to have a very deep integration process. And at this point, my team is working to transform a single board computer on a single chip computer. That we believe is the key technology that Brazil needs to have to be a player in this global arena. So the process is a bit more complicated, but we go to all these domains. We can design applications, we can design SBCs, we are designing chiplets, we are designing the chips, we are going to the foundry, and then the board, the chips, the chiplets, and the wafers. I will say that we're not too far. I even should say that the problem is not economic anymore. It's not more technical anymore. For the Brazilian standards, the problem is economical. We need to have a business plan to sustain this process. I see our engineers here. I don't see any problem making this viable. It's a bit complex. We need to organize ourselves. I claim that we should have national networks designing such technologies, but with the quality of engineers that I see along this week, and with the partnerships that we have globally, I don't see that is a big challenge. And then it's very important to talk about the spiral. Companies that succeed in the global market, like IBM, Apple, Intel, Qualcomm, is from the first 4004 to the last Xeon is the spiral, because they combine software and hardware together. So that is the plan. We should turn the spiral, no? We should start with the first chip, and then the second, and then the third, and incrementally improving the technology, guaranteeing that in the end of the day, citizens, they have what they need, that is computing tools with the maximum amount of applications running on it. And then let the human creativity taking place. You know? So one clear example is the ventilator. When I was packing my stuff because the pandemic, one professor approached me, Professor Raul, and said, "Hey, Zuffo, we need to design and manufacture ventilators." I said, "Great. I never saw one before." He said, "You know every transistor in your chip?" I said, "Yes, I do." "Okay, let's do a co-design approach." So the way how we design and manufacture and certify ventilators in less than 100 days was this heterogeneous systems co-design approach that we're practicing our organization for more than 10 years now. And you know, I'm not talking about a toy here. I'm talking about equipment that should intubate someone for up 90 days. And if someone die, I'm the technical engineer responsible. I'm the engineer in charge. So our legal framework related to design, critical instrumentation, goes to my name. What that means, in the end of the day, if someone die, I can be imprisoned. No, my son is a lawyer. He makes some jokes about bringing me cigars and chocolate and other stuff in the prison. No? Because we are on a given point near to this situation when we start to test the ventilators in humans. The first step was training. Before the Navy entered and helped us, we need to test the ventilator in 4 humans. And if someone die, I will be fortunately not in here. No, I will be probably retired, and I will spend maybe 1 or 2 years in prison. And we did it. We manufactured 1,000 ventilators, and we distributed among 70 states in Brazil. But we're doing more. We're using the fleas, tracking tractors in northeast Brazil. So we have a swarm of tractors on a grape farm in North Brazil. More recently, we are doing CO2 sensors connected to small neural networks to measure the biodiversity of Amazon. And of course, we also we love dogs, so we are monitoring dogs. So now is a moment to mention a new family member, the poodle toy. I just announced it on Monday, but I want to show the chip. So what is the poodle toy? As I mentioned before, we lose in 10 years 100,000 engineers in Brazil. Exactly 10 years ago, we have roughly 450,000 engineering students. And this year, we have only 350. So we lose 23% of seats of students in Brazil. So we need to sort about the future generation. So the Poodle toy, it's an Arduino form factor computer, fully compatible. It's fully compatible in terms of hardware and software. It's designed for educational use and tailored for STEAM programs. We have Professor Roseli Lopes here. We have Elena. These ladies are doing a wonderful effort promoting STEM across the whole country. We have a website named Code IoT, where we have more than 250,000 students assigned, but they don't have hardware. Now they have hardware. So our goal is to manufacture 300 Poodle toys, maybe this year. And the beauty of the Poodle toy is fully based in RISC-V, and the magic is running Zephyr. The whole Zephyr 4.0 stack is fully operational here. So all that 100,000 commits are fully available in our Poodle toy. And that is the board. We start up a company. I hope that the company very soon will start to market Poodle toys. So you'll be able to buy Poodle toys in Brazil for your kids. And I will stop here and I transfer to Liza Costa to tell the magic and the engineering behind in this concept of systems co-design.
Tá vindo. Tá. Acho que tem que tirar e pôr de novo. Você pode. Uhum. Ok. Bom dia, todo mundo. Good morning. Yes. So we are presenting the Poodle toy. It has our chip. It's a RISC-V, 32 bits, and we will show it running live. So, okay. Oh.
It has a GPIO.
Okay, yeah. Sorry. Yeah. So we are showing here the GPIO demo. Can you show? So it blinks here. And do we have, what's the other demo? Okay. Yeah, so it's using, because our chip, it has some crypto accelerators, so it's showing it working, right?
Yes.
So what did it do, Ivan? Explain to them.
It has a AES accelerator and SHA-hash encryption acceleration.
Mm-hmm.
And in this demo, it is reading random data from Flash, encrypting, and then reads an expected output from the Flash, and then it compares the two outputs to confirm the correct values.
Yeah.
And then it calculates also the performance within the active cycles and time taken to encrypt the data.
Yeah, so we can see that it's really fast to do the crypto things. It has then an AES and the SHA for hash.
Yes.
Mm-hmm. Do you have another demo for us?
Yes, we have to reset the board, but yeah, that's the 4 demos that we have prepared.
Okay,
for
so
now.
can you show the banner again, the first,
Yes,
the B?
show the banner.
Yeah, so it says, "Hi, I'm Puppy, the RISC-V microcontroller unit, proudly designed by engineers of the Caninos Loucos program at the University of São Paulo. I'm a 65 nanometers processor, compact and powerful, with a silicon footprint of just 6.35 millimeters square, and I came equipped with a cryptographic engines and AI acceleration to power the intelligent edge. Special thanks to MCTI, LSI Tech, IMEC, and everyone who helped make this incredible achievement a reality for Brazilian engineering." Okay, and we have also the AI demo, right? I'm seeing that.
Yes.
Mm-hmm.
So it calculates some Mac operations and calculates the time it takes to process some.
These operations. Mm-hmm. Okay, really good. Thank you very much. Yeah, congratulations. Yeah. I would like to thank also, this is Ivan, Catherine. Yeah. Where is Gabriel? Yeah, we have Gabriel. Yeah. Thomas, everybody. Yeah, yeah. Edgar, Anna. Yeah, okay. Yeah. So, okay. Can you go stand? Okay, now let us go back to the road. Acho que tirei. Okay. So, as Professor Marcelo presented, we have this top-down approach. So we started building some platforms that we used in many projects. He said about the Internet of Things and the project, for example, that we were monitoring pets for the dog scholar. And we did it in this board that is fully operational and is embedded already in some products. And now what we are doing is to develop the chips in order to replace these ones and keep everything working, right? So we already have some applications. We have some use cases that we tested, our board and our system. And we have already all the software stack. And now we are designing the chip for the processor and for the power management unit. So this chip that we have shown here we have it working is this processor. And we used RISC-V because our project is all about openness. So the idea is to have the technology domain, and we choose the RISC-V that has allowed us to have this achievement in this time and with a small team. And our work is focused on edge computing. So all our boards have this target. We are always thinking about low power, high performance computing, but embedded. So the FLI, that is this chip category, we are thinking about applications really low power and harvesting enabled. So this is why we not just focus it on the processor, but also in the management unit. Okay, here is some details about our project. We did 2 versions of our processor. The name of the processor is Puppy. And the first version was sent to fabrication in April 2023. Unfortunately, we had a huge delay to receive it, so our project was really delayed by that. It took us over 1 year to receive our chip after sending it to fabrication, so it was really hard. But we received it and it was working. And incredibly, they had done a problem in the fabrication. So it took us almost 10 months to get it all done. So this is why now we have completely approved. And so this first version we did for up to 20 megahertz. And it has micro DMA. We had a timer, I2C, SPI, WART, camera, I2S, SDIO, and 32 GPIOs. Then in this waiting time, we developed the second version, okay? That's the one that is actually working here, that we added the hardware accelerator and some more peripherals like USB and more units of the others like E2C, GPIOs, and we improved the frequency up to 100 megahertz. So what we did is this high frequency clocks for the second version. And the acceleration, we used the AES, SHA-2, and SHA-3. We had the USB, SPI, and WART, more interfaces. And this is our architecture. And we did some validations for this core. So for core Mach, we have 3.12, that's really good, going up to 100 megahertz. And we did a lot of stress in memory, interface, power consumption, and we are really proud of the results. We could get 101 MIPS for memory access performance, 101 for ALU, and the peripheral, 64 kilobytes. And we did all this, and it worked very well with the temperature stable. Yeah. So we are confident of our robustness to go to the market. I was talking about that with Professor Marcelo this week, that we totally want to push it to our products that are already in the market and new ones. So, yeah, this is some of the comparisons. For example, with Sci-5 E20, it has 2.5 of core Mach, so it shows our performance that is really good. And the power consumption, that its tops is 3.5 milliwatts. And you can see here that with the DMA that we have, the direct memory access, we can have a lower consumption, power consumption, but it's all really, really low power. It's in the maximum, right, with all stressed out, then we have this measurement. We did some tests also with the acceleration for artificial intelligence. As our edge computing applications, we usually have AI demand. So the core puppy, without this acceleration, we could have the same processing. It was, for example, 47,000 clock cycles. But with this extension, it's 30,000. So this is one extension of the RISC-V, right? That is the single instruction multiple data. And you can see that it's really considerable. It's almost 50% more capable of the performance improvement. Okay, here we can see the comparison of the AES CTR mode. So with this acceleration that we have shown for you today, we can see that the time for doing it by hardware is really small, right? And we had a really good gain. Comparing, for example, with Arduino Uno, it's almost zero our time doing it by hardware. The SHA, that's hash, the algorithm for hash also. We can see here the puppy, that's really small, it's the last one there. And yeah, system running here, the whole energy consumption for doing the cryptographic functions. Okay. And another really important thing in the project is the energy, as I was saying, that we are looking for projects in the Internet of Things, and we should be capable of receiving energy from multiple sources. For example, batteries, we could have solar energy and any harvesting, and multiple at the same time, right? So we developed this management processor for energy. So it's an analog device. We have the battery level measured by ADC for a converter from analog to digital. It's important also because you need to know which source has more energy or no in order to do this management and choose what is the source of energy that will be used. Also, for example, we have some sensors that when you have low, the powering of the battery is lowering, you start to have the wrong measurements, for example, from the sensor. We have one that's for CO2, and it always happens. So it's really important to know the battery level to have a good system. And yeah. So it will regulate the output, right? So to have the processor with the right tension, the right voltage input. Yeah, because when you are doing harvesting, you will have the energy will not come out with the correct energy. For example, 3.3 volts if you need it in the output. It's 1.8 volts, right? the output of the PMIC. So you may have this variation in the input when you are doing harvesting. So it's really important to be able to correct this energy level. And this is what this block does. Okay. Yeah, this is the chip. So it's an analog block. It's full of these challenges that we were working with. It has some analog cells with 1.8 volts, I/O cells, and it is programmable with I2C. So it's possible to the processor to configure these harvesting sources, and when it wants to, for example, I want to receive energy from the battery and use and continue working. When the battery is about 20%, I will stop and I will turn off because I don't want the battery to go to zero and then damage the battery, for example. So it's a really interesting feature. And this is really innovative because we have these switches and this selection of multiple inputs, and it's really nice. So, and the analog to digital converter, we use also to feed the processor. So we can use it not just for the power inputs, but also for measurement of sensors and other information from the environment. Okay. I don't know what I missed. I forgot, but okay. I don't know if we missed anything. But okay. So here is our roadmap. So what we have here is a roadmap for the next years. We have now just released the Poodle toy that's using Puppy, our RISC-V processor, and the PMIC, right? That's the energy management unit. And we are integrating these devices into chiplets, as Professor Marcelo explained, the system on chips, and put it inside our main boards. So we are integrating the two main chips of Pulga and put it into a chiplet and then into the board. And we are using this course in order to do an acceleration of artificial intelligence acceleration. So I will explain later that we have this matrix of cores that are helping us to process the convolutional network layers. And it will be part of this chiplet that will go in then to Labrador. Labrador is our mid-range board, and we use it for example, we have a camera. Oh, yeah. So, yeah, this is, and we use it for computer vision. So, for example, with the police, we do license plate reading with this board. It's really impressive because it has 2 GB RAM memory, and we can do deep learning, and we can read license plates, we can recognize, for example, guns, people, and we use it to automatically generate alerts and send to the police or to the tablet inside the police car. It's really nice. Okay, so now I'm talking about Border Collie. This is our new development that is ongoing now. So we are developing this chip of this board entirely here in Brazil. And we have been doing it, and we believe it's really important to have this AI acceleration improved more than Puppy. So we are working on that. I will explain to you, but one thing that's important is to have really low power also. So we have now less than 1 watt, and we want to keep it. It's fully compatible with Debian, so we have all the applications and the facilities to, and the programmers and the usability from the developer side. Yeah, and all our devices are made to be connectable and be seamless integrated one to the other. We will do this acceleration with NPU and using, of course, the RISC-V instruction set. Okay, so one requirement for our neural processing unit is to be flexible, right? Because our platform, it's embedded, but it has this deal of general purposing unit. So we want this board to be able to be integrated in any IoT devices, right? So this is a construction block that can be put inside the products, right? It can be dash cam in cars, as we did with the police. It could be the ventilator. And so we were focusing on this flexibility for our neural network accelerator. And we came out with an architecture that is heterogeneous. And we have some accelerations from specific instructions until having this cluster acceleration for matrix multiplications. And we have also this vision of having some reconfigurable blocks. But we are having some problems to have it integrated in the processor now, but this is the plan. So we would have these 3 layers of accelerations. And what we are, so we have here the dedicated acceleration that would be like an instructions extensions, and this cluster of cores. And our idea for Labrador is to have really simple cores for this matrix. So we have this cluster, and having a more powerful processor to do all the program normally. Okay. So we have now an implementation in FPGA, and we did here a comparison. And using this cluster with just 9 cores, we could have a really great reduction in terms of clock of about 10 times. And our idea is to have more cores. We are still evaluating the best option. But one thing that we are working a lot in this point is to develop the software architecture in order to have a seamless integration from the developer to our hardware. Okay, so this is it. Thank you very much.
So thank you for both speakers. Congratulations to the whole team. Anybody that's in the room that has done any kind of complex design, know that there is lots of work behind what we just saw. Any questions or comments?
I have a question about your crypto acceleration. I noticed there was a series of different crypto algorithms up there. And because of the movement towards quantum resistant encryption, I was wondering if there's a capability of incorporating NIST algorithms that would be quantum resistant into the acceleration.
Well, there is a requisite idea behind, because 10 years ago, Brazil implemented our national digital certification infrastructure. So the criteria to select these algorithms is because the banking system, our banking transfer system, PIX, they are all using these algorithms at this moment. So Brazil is standardizing now post-quantum cryptography. And we doesn't see if that's the problem, because we are the group who certify all digital certificates in Brazil for the past 20 years. So since we really are committed to go to market with this technology, our first approach was to implement the crypto algorithms that will be adopted by the Brazilian banking system. And as the technology evolves and the standards evolve in Brazil, and there are several discussions about post-quantic cryptography, we are committed to deploy these algorithms too. So we are tuned. Our team is small. Remember that the magic behind we reaching this fast pace is the system co-design approach, where in the beginning we have some reactions, but the guys from software talks with the guys from operating system, that talks with the guys from design, that talks with the guys from manufacturing. We have a lot of tension among them, but in the end of the day, you see that we can do chips very fast. And Liza, I want to comment too.
I want to talk about that phrase that he said, that I think it's fantastic, but just because it's, if you are really serious about your software, you should do your own hardware. And I think it's the same for the hardware designers. If you're serious about your hardware, you should do your own software as well. So, for example, our hardware designers, they are always doing drivers and porting operating systems, and they have to work with the precompilers because they are really, they know how the hardware works, and they are the best ones to do the software in order to use it. So we, in our team, we have also this needs to be flexible. And when we talk to someone in order to work with us, we say, okay, but are you okay if the person is specialized in verification? Then is he capable? Are you open to do other stuff? Would you do drivers? And people say, yeah. So
Your answer was perfect. I only wanted to ask because I know the power issues around encryption, and particularly when the same encryption may be used for disk encryption, it may be used for firewire encryption, it may be used for the equivalent of a VPN. And so your ability to cut down on the power consumption by using your crypto chip was impressive. And I would like to get certain organizations working with you now to make it impressive for quantum computing encryption.
okay. Thank you very much. Yeah.
Okay, seems like that we have lots of conversations to be had with the team later. So, but thank you very much, Professor Zuffo. Thank you, Liz, and thanks for the whole team. Okay. I believe that we have another section starting right away. Who is the chair for that section? Liza, you are in charge now. Yes, right away.
Okay.
Vou. Okay, you are Cheng. Cheng. Go there, if you find them, just escape. And that's the Google Drive, yours should be there, right? Let me see, if it is one. No, there's no.
Here we go. Yes. I need to find my name. Yes. First one? Cheng. Yes, here. Yeah, Cheng.
I don't know where
Can I move on to the next page? I use this mouse or something.
And you have also the password
Okay,
there
okay.
if you want that.
Yes,
you,
yes.
you can do both. Download. Cool. Okay, it seems that.
Yes, thank you.
Okay. Second, let me see who is the second speaker. Do you know Shou?
No, but she's here. They,
We should prepare her slides.
okay, their
now.
slice is there. I don't know. I think it is Sue. My name. But Sue has two talks. I do not know
No,
which one of
This
them.
design officer, the ship's officer,
She had another yesterday. So I'm not sure.
Is she here? Are you seeing? So we're gonna do yours now and
Okay.
hers later.
Bishop. So, yeah, this.
Okay. Here.
Okay, thank you.
So it's 15 minutes and
Okay, okay, no problem.
so how do I pronounce your name?
Cheng Shuyao.
Cheng Shuyao.
Yeah. ICTCA.
Chinese Academy.
Yes, yes, the same.
Hello, everyone. Let's move right into our next section, Intelligent Optimization in EDA. Okay. Our first speaker is Cheng from the Institute of Computer Technology, Chinese Academy of Sciences. Thank you.
This one.
This one? Okay, okay. Hello? Okay, okay. Hello, everyone. My name is Cheng Shuyao. I come from ICT CAS and also the State Key Lab of the processors in China. And today my topic is data-driven logic design automation for processors. Okay, let's try this. Okay, sure. Let's start first with the background here. About the logic design and logic design automation. Our project's name is Qimeng. It's a Chinese word. And what it is doing is about program the HDL codes without human involvement. Our goal is to design an AI engineer for logic design and logic verification. It starts first from the design requirement. Maybe for processors, it's the ISA file, and its output is the Verilog code, which can pass the verification, and meaning that it is functionally correct. Our motivation is that the logic design costs most of the manual effort in the entire chip design flow. And we have a front end from the design requirement to the RTL code, and we have a back end from the RTL code as a start to the GDS, which has synopsis, cadence, a lot of EDA flows here. And it does not take a lot of engineers, a lot of humans to do this kind of things. But in the front end, from the ISA file, we need a group of engineers to program the circuit logic into the HDL code, the RTL code, and another larger group of the engineers to verify, to help debug the designed RTL code. And finally, it may and may not pass the verification, and we output the correct Verilog code. So 60% to 80% of the entire human involvement in the entire chip design flow is in the front end, is the logic design. So we're trying, I'm sorry? Okay. We're trying to make the logic design, the front end, automated. In this way, we can get an end-to-end processor design flow from the very start point, from the design requirement, the ISA file, and directly to the GDS, which what we need is an AI model. It can write the RTL code from the test cases, just come from the ISA file, and self-debug and pass the verification and get the correct RTL code. What we did since 5 years ago, back in 2021, we designed a RISC-V CPU from the ISA functional specification only. All the Verilog codes are automatically generated. It contains over 4 million logic gates, and it is extremely accurate. It has about 13 lines here, and it was taped out back in 2021 in December, and it can successfully execute the modern softwares, such as the Linux OS, the spec benchmarks, something like this. However, the design, and it is not the same as on my computer. It is blocked by the figures, I'm sorry. And you can find my whole slides on the website, so I don't think that's a big deal. I'm sorry for that. Back in the 2024, last year, we designed a superscalar RISC-V CPU with the same input, same output, without any human involvement there. And it contains over 10 million logic gates, and it is manufacturing. It is now in the fab, and it would come back this month or next month. It has a big delay in the fab. And its performance is about over 300 times than our first design, the Chemo #1. It is comparable to the 2010 CPU as the ARM Cortex-A53. It has come from the idea that the dependent data can be forward and speculated, and we designed this kind of, we may call it a modern CPU here. And in the future, from 2027 to 2030, we are going to make more progress in introducing more and more currently manual knowledge about the computer architecture into our AI design. From 2021 to now, the red strategies from sequential FSMs, the pipeline designs, the multi-issue units, the target and value prediction units, the cache, of course, they are all introduced in our current AI design in the Chemo #2. And in the future, we are going to add more. For example, the out of order, like to Marcelo, something like that, and the ISA extensions. And at least we are taping out 2 more CPUs without human involvement, the whole RTL code generated by our AI method. So today, the AI design is worse than the manual design in all 3 kind of things, the performance, the power, and the area. So there are questions to be answered. Can AI design better processors than human experts? At least any possibilities in our near future. And we make it more specific, 3 sub-questions about the functionality. Is the AI accurate enough? So we know that the neural networks, transformers, GPT, they are maybe not reliable, not sound. So can we trust them for the taped out CPUs, processors, or something like that? And the other question is about the quality. Can AI really outperform the human experts? And yesterday, there was a discussion in our keynote from Professor Cheng about that whether AI is just memorizing. What if there are no enough training data can be seen by our AI model? And the third question as well, can AI really create unseen designs when we are really lack of the data? And let's try answering these questions. The first is about the functionality. Is AI accurate enough? For a chip design, a processor design, if it is 1 GHz processor, it maybe can execute about 1 billion instructions per second. And if the accuracy is about 99.9%, every 1 microsecond there would be a bug. It is nothing. It makes no sense. But 99.9% is a quite high accuracy for the AI method, for the AI tasks, such as the image recognition, object detection, speech recognition, QA systems, this kind of 90% accuracy. If you see an accuracy such as 99.619 the accuracy, it usually means you're overfitting. It means nothing. So an based method might not be a sound might not be sound enough for us to design a chip like this. Oh, wow. What happened? Yeah. So we propose BSD, a probabilistic symbolic model for the logic design. It is difficult for us, at least in our opinion, to hit 100% formally correct circuit in one shot. So we design iteratively. We try to output a series of HDL codes with more and more logic gates in it. And theoretically, we prove in our paper that for any combinational circuit logic, the BSD model can generate the next design with not only larger, more nodes in it, it is also more accurate than the current design. And any discovered mistake can be formally fixed. And the accuracy is convergency. It means that for any epsilon convergent to 0, the BSD model can ensure a design whose accuracy is beyond 1 minus epsilon. And there is another line down there, but something happens, I don't know, so you can see that. It says that the computational complex is around the linear, yes. So we tape out our first CPU, Simon number 1, to prove that our AI method, the BSD model, is accurate enough to design industrial scale CPUs. It can design industrial scale CPUs, so it can design something else, some units, ALUs, or something about the controlling part in the entire processor, and we make some applications of it. And there are also downsides. It is quick, it is accurate, but it's not good enough. The quality is not good enough. Qimou number 1, its performance is about it is blocked by the figure. It is about the 1990 CPU, about Intel 486, something like that, but it is far larger than it. So there is a real gap between the machine design and the human design. So that leads to another question. Can AI really outperform the human experts? Here we show a figure from our textbook. It's a Marcelo method. It is proved in the textbook that it is the perfect out of order technology in the CPUs. And we want to ask a question like this, that can AI really break the performance ceiling in the textbook with its ability to design functionally correct variables? In the textbook, they teach us how human to write the RTL code, to design the computer architecture. But AI is different. We do not know what pattern it should be, and we show some cases here. Our answer is yes, at least in some certain parts of the processor, we can find a better design from the AI than the human designer. Our insight is that the AI can get a much fine-grained space. It is a larger design space than the human designers, so it may find a better design. There are 2 facts here. First is that human designers do not read all the netlist details. They usually read the input port, output port, the data path, something like this. But like the logic synthesizer, the placement, the routing, all the EDA things, they can do better than human because they know more details. The second fact is that human designers, they do not usually afford to heuristically search for better quality design. Well, there is another line down there, but we cannot see it now. Let me make an example here. If we can write 1,000 very different HDL code, 1,000 very different RTL code to find about 5% of the performance improvement, it is not usually affordable. But for AI, you just leave it in the data center and let it run. That's it. Here we give an example. The example can also see in our paper. Okay. And it is about the hardware scheduling. It is a kind of thing we think that it can avoid the data and hardware hazard and in the pipelines, in the cache, and out of all the controllers. In this kind of things, AI method can design better than the human. This example shows that we have 2 instructions here. The second use the same result have to be calculated first. And if we are human designers, we know it's read after write. The pipeline has to be stored. But if we look deeper into the netlist, we can see that the read after write data path, the gate level signal path is not validated. So it can actually, in parallel, execute it, and it can save the redundant store in the pipeline. It can execute better than the human designers. And it is a three-step way to execute it. And it first search for a better quality solution. The solution might not be easily implemented on the hardware because it might be a neural network, it might be a C project, it might be something like that. But we do not need a human to implement it on the hardware to write HDL code. We can use our AI model to automatically do that. And it is accurate enough, we can verify it and output the exactly correct Verilog code. And this is the result in our paper. We do find better than the best in theory human design actually in the textbook in theory, and more details in our paper. And use this kind of AI hardware scheduling, we do make the super scalar RISC-V CPU and significantly improves our performance. And the third question is about, can AI create unseen designs? It's about the training data. In fact, our answer is that the large-scale data in the verification and heuristic search, it do not rely on the training set. For a very small float point adder, it's about 1,000 logic gates. It's very easy to get GB level data from it, and over 1,000 different HDL designs as well. And what can AI do and what cannot AI do? We are doing an ongoing student project in our university. We are doing a library. We want to examine what kind of the circuit can the AI design and what cannot. For example, float point unit, it is very challenging for our AI, but you see an adder, an ALU, it is very easy to design. So we want to test it on an open source tool. And we will release a design tool, a verification tool, and an evaluation tool on our website. And our design result, the IPs, just like the design well front end IPs, will be open source. And coming soon is our EDA tool for automated logic design. You need to input your functional specification. What do you want for your circuit? And this tool will give you the Verilog code, and you can give it some options in your profiles. For example, what is the PPA requirement? Do you need to pipeline it or something like that? There are some technologies in this tool. We read some papers about it. It's mostly about the PPA optimization by the AI method, how it can outperform the human designs. First is about the area. And the second, there's something about the FSMs, about the controlling part in the processor. And let's do it quicker. Why do we design RISC-V CPUs? The most important reason is that it has really good software support on, it is open source on the compilers, the OS tools, and some hardware software interface standards. That means that we only need to focus on the hardware and not anything other than that. Okay, let's summarize. Our topic is the data-driven logic design automation for processors. We try to design the HDL code from the functional specifications. It can be explained by the I/O examples, truth tables, or verification codes, or something like that. We propose a probabilistic symbolic model for the logic design. It is fast, it is accurate, but it is now not as good as the human designs. But it is applied in some of the design flow, for example, the pipeline design, for example, the multi-issue unit, something like that. They can find better designs than human experts. And we are ongoing. We are trying to tape out some more CPUs with better performance in the latest several years. Okay, thank you. And I think it's Q&A time.
Thank you, Cheng. So since you are running a little bit late, I will have time for one quick question, and then we can take a conversation during the coffee break, okay? So any questions?
Thank you for the presentation. I understand that the AI model can like design a chip for a specification, but if you have already a very low code, can it evaluate to see what components the RTL code produces or not? Have you tested it?
It is optional. It is not necessary. And the problem is that it is not as good as the human design. So if you provide some of viral code or something like that, it is difficult to optimize them from here. Yes.
Thank you.
Thank you. Let's do this speaker again. So please. Which is for to take. This one, okay. Mhm.
Yeah, a little bit lot. Am I the biggest one? Yeah. It's okay. 37.
Não foi. Tudo que tá no download ali, não deu. Muito grande. Pode pagar tudo, acho. Pelo menos dos últimos 2, 3 dias. Precisa de 280 megas.
tá no disco D.
E é grande pra caralho. Não tá tendo espaço. Você quer dar uma olhada? Ele tá apagando.
Não, tá faltando espaço no disco C. O download tá no disco D. Tem bastante espaço.
Então, espera aí.
Não falta mais. A não ser que passe para outro navegador. Pelo Chrome tá indo pro disco D.
Mas ele tá dizendo que, né, que não cabe. Só que a apresentação dela tem mais de 200 MB. Agora tem? Eu tentei fazer assim, mas não foi. Do jeito que você falou. Olha lá.
Tá fazendo pelo Chrome?
Tá, pelo Chrome. Olha lá. Agora tá.
Agora tem 1 GB.
Okay. Presentation is a little bigger than we expected. We had a space problem. Não abre. 300 MB. Okay. Okay.
Okay.
Okay, so our next speaker is Zuffo, and she's gonna talk about design open source chips with open source EDA tools and IPs.
Thank you.
Go ahead.
Thank you for introducing and sorry for the waiting. And my name is Xiaoke and it's me again. Like yesterday, I gave a talk of the one chip here. And today I'm gonna introduce a new topic on the designing open source chips with open source EDA tools and IPs. And firstly, I'm gonna introduce our big team. Like we are a very big team from China, like combines members from ICT, BOSC, PCL, like over 100 persons. And we are on the leadership of the Professor Bao. And yesterday, Xiangshan have already been talked. And IEDA, I think the AI EDA will be like give a presentation this afternoon. And our like ecos team under this big team is like made by the ecos, which is EDA, chip, OSOC, and system. And I'm in charge of the one chip, but today I'm gonna introduce the snow part, which snow means like shuttle no weight. And next page, yeah. Our team aim is to like have a full stack solution for the ASIC, and we tape out like more than 10 chips every year, and cover from 130 nanometer to 28 nanometers. And we serve students and several instructions like the OSOCD, and we developed the Eco Studio, which will be talked like today. It is like a cloud-based EDA platform. And this is the highlight and the outline of my today's talk. So the first part, I'll explain what is Eco Studio. And the second part, I'm gonna introduce the education-oriented chip, Rachel Sock. And the third part, I'll tell some latest information or the upgrades of our EDA tool chains. Okay, the first part is like why we develop the Eco Studio. So firstly, this is a cloud-based, agile EDA platform, and we want to get more students to excited about open silicon design, like they can use them to like have a chance to know what is that. And secondly, to fill a gap between industry and academy. And the third one is to erase the performance difference from the local computer because we are using a cloud cluster. So to provide an open solution for the potential commercial markets. And this is the quick view of our Eco Studio. And you see for the first part, like you can select the SOC template from the IP market, and there is an advanced extensible layout editor at the right corner. And we support the real-time collaboration, and you can merge to the latest shuttle. And here is the dashboard, the synthesis flow, and the float panel system here. And here is the part, like some of the key processes like of our Eco Studio and their video playing. The first step is to create a project. Like this kind of video are made by students like who study OSOC for several months, and he tried this process. And for the creation project, like firstly, you need to fill a project name and add some social information for the collaboration or sharing with others. And the third is to select one of the silence you preferred, open source silence. And the second part is to run the placement. Like you'll start the process and there will be some report display here and show some congestion hotspots, and you will know what is the potential issues. And the third part is to run the clock tree synthesis, and it will just start the process by a single click, and you show the animation because you can clearly see what is that, and then some inserted buffers will be highlighted here. And the next step is to show the DRC, the design control. And the first step, you start the process and it will just automatically like display the def file. And then there are some marks of the DRC marks, and you will see, okay, what is the layout issues? And there's a random engine of the Eco Studio. It's called the Advanced Extensible Layout Editor. So this is the key component of our studio, and we support the dev file and highlight the operations. So here are some performance evaluation information here. And our technical roadmap is like we're gonna support the LAF, DEF, and GDS format in the future and improve the performance, of course, and integrate and support the NG-SPI simulator. Okay, for this part, like maybe next year, we're gonna have or develop the VS Code plugin or the desktop client to make everyone or make our users to have a more comfortable design. And now I have a good news that a new OpenPDK in China is gonna like going. So it's called IC Sprout 55 nanometers. And this is a Chinese foundry. I found it in the 2021. It's like from the Zhejiang province. This is one of the province in China, and made by the Zhejiang government and the Zhejiang University. So they're gonna open its 55 nanometer CMOS PDK in this July, like this month. And here are some like MPW tape-out cost of it. And we are trying to bring this IC Sprout 55 nanometer open PDK into our Eco Studio. And we developed the open source, the PLL and the DDR3 file based on the IC Sprout 55 open PDK. And how to bring the users to our studio. Like firstly, we have the students from One Student One Chip, and they are the first batch of our users. And they make tape out a single cycle processor when they finish the learning stage of DE. And the others, like for the academic or individual users, we might invite them like start from the 2026 is next year. So after the first batch, we're gonna attract more users to use. Okay, here is the open silicon curriculum system. Like on the left-hand side, this is the One Student One Chip, like the handouts, context, like I introduced this yesterday. But for the for the right-hand side, this is the backend, like the backend part I also mentioned yesterday. It's about to teach the SoC and the physical design with the Open EDA powered by our Eco Studio, and like some transistor circuits, some SoC design and physical design. So the first version will gonna be released like I think at the late of this year. So we have some considerations here, like what if like there are 500 students want to sign up, and how many TAs are required, and how long will it take to handle? Or what if like over 1,000 or over 1,000 all around the world? So we have a question like, how can infrastructure help accelerate the promotion in shortest possible time? So here's the infrastructure. We're using the complete open source tool chain, like the RITE, and developing the LMSS centric website. And we have like more learning support like the TAs I mentioned yesterday. And here are some new projects we're gonna have like later this year or next year. And we aim to provide the post-silicon education in the future and shorten the development period. Okay, the next part is the retro SOC, the retro SOC. This is a customized ASIC for the retro stuff, and it's an open source SOC framework, and focuses more on like retro game console or full frame CMOS camera. And it's already taped out like a real chip by using the open PDK. But this one is a very long-term project. So it's gonna be supported by our team, by the Ecos team, like long-term. So why we build the retro SOC? Because we want our IDA, I'm gonna talk later, to test if IDA is capable of testing or designing. So here's the technical roadmap for retro SOC this year. And here are some multimedia IPs development plan. So this part I'm gonna go through very quickly. And here's the performance optimization. Yeah, there is a video in the right corner. I think there is a time delay here. Yes. And the next part is about IDA. Like IDA is a full flow from RTL to GDS part. And it's an open source EDA infrastructure and tools. We started from 2020. And we developed the chip compiler based on the IDA. And I think for this part, you can have the afternoon talk later. They will give more details. And here is the physical design tool chain of the IDA. And the latest updates, we enhance the DRC checker. Like we support our DRC rules in just like 28 nanometer nodes. And we compiled that we improve the accuracy and the time. And we enhance the timing optimization flow. We use like 50 data sites, and we have like better in performance. And we also integrated the IC Sprout's 55 nanometer PDK support into IDA successfully. So that's what we do. And there are latest the tape out with IDA, like nutshell, some SOC, and the others. So moving forward, what's our future plan? Like we would like to improve the performance and the quality of the Eco Studio for sure, because this is our like one of the most important work this year. And for support more foreign students, we would like to support foreign students with the OSOC and with the backend part. And the others, we want to get more involved in the international communities of like open source communities and sharing our ideas with others or communicating. And the last, maybe we try to redefine some cultural, creative products and try to make a gift for you, maybe next time. Yeah, and here are like some events we attend this year, and we are now in Grow, right? And currently, one of my colleagues, like he's in FISC 2025, is in Germany, and the next very important event for us is RISC-V Summit China, and we're gonna release the first version of the Eco Studio here. So the time is July 16, and yes, follow us. Maybe we'll share the good news at that day. Okay, so that's end of my presentation, and here are like some main contributions of the whole Eco Studio and the IEDA. And if you want, you can just have their email and maybe contact. Thank you.
Okay, one quick question. No questions? So we had another speaker following this, but it would be remote, but he couldn't make it till now online. So what I'm gonna do is, since we have a keynote that cannot be delayed, I'm gonna reach the speaker, ask him to record in video, and we are gonna put in the website and the YouTube channel after the conference. So it will be available, the content for you guys in the next few days, okay? So this closes this section. We are gonna have a short break now, and 11 sharp we are gonna be again in the next, with the next presentations, okay? Thank you.
Thank you.